ಓಕೆನಾ? ಕೇಳಿಸ್ತಿಲ್ಲ ಅಲ್ವಾ? ಹಲೋ 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 ಹಲೋ, ಮೈಕ್ ಚೆಕ್. ಹಲೋ 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 ಹಲೋ, ಆನ್ ಆಗಿದೆ ಅಲ್ಲಿ. ಇದೇ ಮಾಡ್ತೀನಿ ಬೆಟರ್. ಹಾಂ, ಹಲೋ ಹಲೋ ಹಲೋ, ಮೈಕ್ ಚೆಕ್. ಸರಿ ಬರ್ತಿದ್ದಾ? ಇದು ತೆಗೆದ್ಬಿಡಿ. ಹಲೋ ಹಲೋ ಹಲೋ, ಮೈಕ್ ಚೆಕ್. ಹಲೋ ಹಲೋ ಹಲೋ.
ಇನ್ನೂ ಬರ್ತಾ ಇದೆ. ಇನ್ನೂ ಬರ್ತಾ ಇದೆ, ಒಂಚೂರು ಬರ್ತಾ ಇದೆ.
ಎಲ್ಲಿದೆ ಅವ್ರದ್ದು ಇದು ಮೈಕ್ ಸಿಸ್ಟಮ್ ಅಲ್ಲಿ ಅಲ್ಲಿ ಸೆಟ್ ಮಾಡಿ ಗುರು. ಇನ್ನೂ ಸ್ವಲ್ಪ ಬರ್ತಾ ಇದೆ.
ಹಲೋ ಹಲೋ,
ಅಲ್ಲಿಂದಲೇ ಬರ್ತಾರೆ. ಕ್ಯಾಮ್ರಾ ಬೇಕು ಕಾಪಿ.
ನಿಮ್ಮದು ಕರೆಕ್ಟ್ ಇದೆ ಅಲ್ಲ? ಆನ್ ಮಾಡಿಬಿಟ್ಟಿದ್ದೀರಲ್ಲ?
ಗುಡ್ ಈವ್ನಿಂಗ್ ಒನ್ ಆ್ಯಂಡ್ ಆಲ್. A warm welcome to the third lecture in this Dasara Lecture Series 2023. To begin with the today's program, as you know, today we have a very eminent scientist with us who is giving a talk on strategic asset in the pursuit of revolutionizing the world of materials. The speaker is none other than Professor Ranjani Viswanatha, who is a professor at JNCASR. Before I introduce the speaker to you, may I now request our director, Dr. B.R. Guruprasad sir, to welcome the gathering.
Yeah. Good afternoon to all of you. My presence is only contextual here, okay? Anyway, since it is formal, I formally welcome you to this third lecture in the Dasara Lecture series, Popular Talks for this year, 2023. And first lecture being related to the scale, distance scale in the universe. Yesterday it was a little bit different in biology. Today's one has a very, very attractive caption, in fact. I thought it was something to do with international relations, first part of it, because size a strategic asset. Okay, this is the thing which is used in political science many a times, and international relations. Size a strategic asset in the pursuit of revolutionizing the world of materials. Of course, very important in our daily lives or even elsewhere. What role materials play? That is the one which is being discussed. Many important and popular things, as well as things of significance related to this, the speaker is going to discuss. We are highly thankful on behalf of BASE, Bangalore Association of Science Education, administering the planetarium. We appreciate the presence of Madam Ranjani Viswanatha, Professor Ranjani Viswanatha, for giving a talk here. And now I request Anand to announce, Anand or Sharanya to announce the next event. Thank you. Thank you very much, madam, once again.
So it's an honor really for me to introduce today's speaker, Professor Ranjani Viswanatha. Ranjani Viswanatha is currently working as a professor at Jawaharlal Nehru Center for Advanced Scientific Research. She did her PhD at the Indian Institute of Science. Subsequently, she worked as a postdoctoral fellow at Professor Zhigong Peng's laboratory at University of Arkansas and at the Los Alamos National Lab in Professor Victor Limos group before joining JNCASR. She is currently a professor at JNCASR and she works in the area of quantum dots. Her work has been published in leading journals, and she has been awarded several national awards like Sir Power Fellowship, Karnataka State C.V. Raman Award, MRSI Medal, DST Young Nano Scientist Award, Sheikh Sar Fellowship, founding member of Indian National Young Academy of Sciences, and also she is the winner of the INSA Young Scientist Medal and chosen as a Young Associate of Indian Academy of Science. And she is also founder member of Indian National Young Academy of Science, among many others. She is also a member of the editorial advisory board and reviewer in many of the leading journals. And she has given several talks in leading conferences. Apart from this, these are her academic credential, which is really big. But apart from that, there is one special thing about her is she is also a student of REAP. So JNP is very proud of you, ma'am. She was a REAP student who did the REAP course here as you. So we are very much close to her, and also she is associated with many of our academic programs, and she has been very helpful in conducting many of our programs. And as she is serving here as a resource person in many of our activities. And we thank you for that, ma'am. So, let me now request our director, Dr. B.R. Guru Prasad, to hand over a token of, a memento as a token of gratitude. Please, ma'am.
Thank you. Thank you.
Now I request Professor Ranjani Viswanath to take over the dais. Thank you.
Thank you. Before I get started with the talk per se, I'd like to express my heartfelt gratitude. I am a child of the planetarium. This thing is mutual. It's not just one way. I was literally probably like his age when I first started here, and with probably the trial show of planetarium, and I have been involved in the planetarium at various capacities, starting from being a visitor all the way up to being a student, a resource person, and in several other activities of the planetarium. So it is my pleasure to be here to give a talk in this very prestigious series that they have started, and I hope I can do justice to it. So this I will get started with my talk. So today my talk is about size as strategic asset in the pursuit of revolutionizing the world of materials. So I was told that we are doing a series on size and scaling, and you need to give something in the area of chemistry, which is where I specialize in. I was wondering like how I can incorporate, although I work in the area of chemistry, specifically in the area of science, to bring it down to this, I was wondering how we utilize that. And the first thing that struck my mind is that more often than not, people don't realize, and which is not unfair on them, that size is a particular asset which we can use. We know that we can change so many other things, especially materials. Like I can change a material to get a different property. How often have we thought that I can change size of a material to get different properties? That's not without background. So Madhusudan very nicely offered to give me this. These are two crystals from the same structure, same material, and if I were to pass this around, you will see that you see these hexagonal structures, though a little crooked, but these hexagonal structures are actually seen in this very small crystal. And as I go along the talk, we will discuss about this, and after that I will pass this along once I am done with the discussion. So when they look exactly the same, they also provide the same properties, and so it's not without background that people think that size cannot be used as asset in getting new properties from materials, which is what we are all worried about. So today I hopefully will convince you that size is something that we all need to utilize. Okay, so let's start with why size matters. So this is those beautiful peaks of Himalayas, and it's probably one of the tallest, if not the tallest peak, it is one of the tallest peak in Himalayas. So why, I mean, we all know that Himalayas itself is one of the tallest mountains, mountain ranges. So, and the sky is so far away. There is lot of space, both up and in the width. So why doesn't it grow taller? Why do mountains be the size they are? What happens? Can someone volunteer an answer? Which is not related to chemistry at all. It's geography. But so basically what happens is there is a movement of the plates. This is what people know about. that there is a movement of plates, and Himalayas grows by, I don't know, I might be terribly off, but I think it's around 8 mm per year taller. Why does it take, what has movement of plates got to do with 8 mm growing in a year? So, the first thing that comes out is this, which we have not really got a very good demonstration, but if you see here, you see what you see of a mountain is just this, but for every mountain of what you see here, there is an equivalent part down below. It needs to push, and if I have a bigger mountain, wider mountain, the push has to be much more, and so you need to get it much lower, much further lower for it to grow taller. So, basically this is one of the reasons why we should be actually seeing this growth of mountains going very, because it's not, it's only what we see on top, but the bottom, there is a huge bottom, and that needs to grow, and that can only grow at whatever pace it is, so that the mountain can grow at the pace that we were talking about. So, size matters everywhere, whether it's a mountain, and okay, mountains it matters, you might tell me that such a big thing you need to matter, but why should it matter on daily, day-to-day scale? I function exactly, assuming a little older child, a smaller child functions exactly as an older child. Everything is exactly the same. The eyes, the nose, ears, mouth, everything functions the same, except they are smaller. So, why should it matter? So, the first thing that comes to our mind is that size matters everywhere. So, let us do one experiment. I have a very young participant here who is very interested. You want to come and do this experiment? So, first, before you do the experiment, can you tell me, guess, so this is 2 times this one, okay? How many cups of water should I put into this to fill this? 1, 2, 3, 10. Any others have any other numbers? I am telling you that this is 10 centimeters big and this is 5 centimeters big. So, how many cups of water should I put? I see a raised hand there. Can you tell me a number? Just tell me a number. I do not want an explanation right now. 5 cups. Okay. 8, 10. Any other number? 4. Any other? 8. Okay, I have 2 8s and 4, 5, 10. Any other? Okay, now what's your name? Vaibhav, please come here and we will give him some water. So, you can put, you fill it in this one and put it in this. You can come from that side. Okay, you can keep it here. So, carefully fill up entire cup and put it in here. Yeah. Okay, 1, 2, 3, 4, 5, 6. Looks like you are going to win, Vaibhav. 7. 8. I think you have not done a very good job, but see, you are actually not filling. So, that actually matters. You have to take it full. By 8 it should be filled, but you have, the answer is 8. We can try it out again, okay? After the class you can try it out again, you should get 8, okay? So the answer is 8. So any idea why it is 8, not 5, 4, 10? Yeah, so the size is double, but when I am saying filling it with water, I am actually talking of volume. If the size is double, what would be the volume? Cube. Volume is a cube. 2 cube, which is 8. So you should have 8. So one thing that counts is that you have this small cube and a big cube. 8 of these small cubes would fit into this. Okay? And that matters. So why should it matter whether, which means that this cube has a little more surface than this cube. Let me just flip the slide. Okay, this is how you would actually see the previous one, wherein we already did the experiment. So you can see here that it only goes down this much, whereas this goes down far more, the mountain experiment. So why should it matter? We will look at it. We have already looked at this, but we'll come back to that. So you see here that surface area, volume is always a cube. I am not changing the size of this cube, just cutting it in half. So if I were to just take A as the length, I will see that the surface area goes as 6a square. If I just cut it in half, it will go as 8a square. If I cut it into further smaller pieces, 24a square, and finally 48a square. So volume has not changed, but surface is changing. What do I mean by surface? What I see on here, this. Why should it matter? You will ask me, right? Why should it matter that what I see here is important? Other than the fact that, okay, if I am talking of catalysis, some molecules come and attract only on the surface. I am not talking of that. That also matters. But why else should it matter? Any physics wise, why should it matter? What is the surface? More contact. What happens with more contact? Shani, where's the switch for this? Okay. While she is doing that, we'll do this experiment while they switch on that. Which one? Let's do this experiment. Can we have the ladder so that we can switch it on in the meantime? The other way around. Yeah. No, here. So that I climb from this side and yes. And I will do an experiment and I want all of you to answer me. Okay, so I am going to drop this. You watch this fall and then you tell me which one weighs more. Okay? By watching this. Shall I put it? Which one weighs more? The sphere. The sphere. Do you want to, yeah, we can have that other one and try it. So if my left hand is probably stronger, let me see. Okay. Shall we do this? Sphere or the flake? Sphere. Okay, so now that you know which one, let's at least some of my friends are saying, young friends here are saying that the sphere weighs more. So if the weighing machine works, we will see which one weighs more. Other way around. Okay. So let me use this hardcore. I don't know if this is accurate to that level, which, no, I don't think you will see it, this one. So I think to go on our seniors' words, they weigh the same, they both weigh the same. And this you must have already felt, like when you see, being in India, being in Bangalore, you probably would not have seen snow, but you might have, if you have ever experienced a snowfall, you would have seen that the snow doesn't hit you like rain hits you. If you have a heavy snowfall versus heavy rainfall, the rain really hits you, like pierces your system, but this doesn't pierce, the snow doesn't pierce. That's because I have a larger surface area when it's a flake. Although they weigh the same, it's a larger surface area. And that's why, so what happens if it's a larger surface area? Physics wise, you will have some pressure, force. The force depends on the weight. But all these surface area, what does it do? It allows it to deflect the weight. So if, for example, if I were to go on to Qutub Minar or Red Fort and jump down, do you think I'm going to crash? Are my bones going to break? Yes or no? Most likely yes, if I'm still alive to check out. But if I drop a small squirrel, let's say, do you think it's going to survive? It's probably going to survive. I don't want to check it out. I don't want to kill the pure. Yeah. Yes. So let's make it simpler. If I drop an ant, do you think it will survive? Yes, right? So, yeah, without any bones broken, you're very right. So, we will, next time we'll see if we can bring some test squirrels and test ants to drop and see. This time I don't have them, unfortunately, but what they do is the force is going to be spread out on the area, and the area defines how this is going on. And further, second thing that happens in these snowflakes is, if you have a large area, there is all this external interferences which helps it to slow down. This is what happens with a parachute. You slow down the speed at which you're coming, which means you slow down the force. So both ways it's working. So it's okay. They've assumed that I am right. And the third reason why I want to reduce the size. Why do I want to reduce the size? So we have all decided reducing size will give me good surface area and all that. But there is another reason why I want to reduce the size. So here I bring in this idea. When none of us in this room were alive, came the first computers, and the okay, so they have switched it on, and I will tell you what is the weight of this. Yeah, now it shows me 0.000, and I have 1.643 grams of the sphere, and this is 1.576, a little lighter. Let's see the other one. I have 1.786 and 1.782. Wow, very good architectural engineering. Okay, so you are convinced now that we do have exactly the same weight, right? Okay, so we'll go back to our computers. When the computers were first put up, this is the image of the first ever computer in 1943, and it could hardly do 5,000 operations per second, which is, believe me, nothing. In today's world, you probably do 5,000 operations in 1 nanosecond. Okay? And for that, it's 10,000 units of 100 grams, which is about 1,000 kilos. What am I talking of 1,000 kilos? A metric ton for a laptop, if you can call it a laptop, 1,000 kilos. I don't think I can lift that. Forget about carry it everywhere, I don't think I can lift it. So we need to reduce size. Okay, so and changing size has changes on the surface area. So we are aware of that and we want to see what effects does it have. So let's, we need to be able to use and manipulate down to the atomic and molecular levels. So let me see what I can do at an atomic and a molecular levels. All of you in various stances have seen the Velcro, like this. All of you have seen a Velcro. What does it do? You just rip it apart and rip it together. Okay? It works perfectly. How does a Velcro work? It has these rings and it has these hooks. And now let's try to do it on a better scale so that we can see the rings and the hooks. If someone can help me with this. So you see that there are these hooks. I want a little bit older person for this. Yeah. So you have the hooks. This is one side of my Velcro and this is the second side of my Velcro. So can we just try and see if we can make it. Okay, it did stick to some extent, right? It stuck. But can I remove it? Not so easy, right? So yeah, I am stuck. Even with a smallest ones, I am stuck. So thank you. So size is very particular and Velcro is not the only thing. If you were to see, nature is much more better. I don't know where I am keeping these. So why did it change to this? Did I do anything wrong? Why did it change to that? Okay, there it is. Okay, so if we are to actually go down to a microscope, but a microscope wherein it's so small that I cannot even just do it by optics like I do it with an electron microscope, then I can see whatever that small chip here is actually made up of this kind of structure. And where do I apply it? I just see what is it made up of and you see like a Velcro would look like this. And where else can I see it? I can just take a lizard's leg and put it in the microscope. Other than the yucky part of it, forget about the yucky part of it, you will see it looks actually like that. The leg of a lizard, it would first look like this, exactly like your Velcro. But if I were to go and expand this even further, there is this kind of a structure which helps it hold on to the wall. And obviously if I were to wear a Velcro dress and go and try to stick onto the wall, I am not going to work. Size matters. Oh, okay, we all agreed that size matters, but if we have to utilize something with the size, we need to know how strong are these forces. If they are very, very weak, then I am not going to be achieving a lot. Okay? So in order to check how strong these forces are, we have done a specific experiment here. I need about 8 people or something, so strong people, 8 strong people, volunteers, so let's divide you into kind of equal. Okay, so come. So I have you, can you come on the other side? And can you come on this side? And then one of you on this side, one of you on the other side. You can come here, or you can come here. And you can go and sit because I need exactly even number. One of you can. You have done one experiment, right? Okay, hold it. And can we do a tug of war? Yeah. Tug of war. Careful, careful, okay? Okay. Okay, good, 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 good. So, who's the winner, you think? This side or this side? This side? I really don't think. You know who the real winner is? The books. They're not held, they're not pinned or anything. I just need to do this. You see? The books are the real winners. I can actually separate the books and give a lot more work to the planetarium people for redoing this. What? These are telephone directories. Yes. We just took the telephone directories because the papers are very thin, and thinner the better. Thank you very much, all of you. And you see, I think the real winners are these books. You see, I had not held them together with any of the forces or any glue or anything, and they didn't break apart. We still had a reasonably good tug of war. So, yes, and I was more worried about them falling off the stage. So, yes, it does have very strong forces. The reason they didn't come apart is because when you go to smaller sizes, the interparticle forces are very, very strong, and you can actually make use of them. So, where can I make use of these mechanical properties? You can, first of all, they are very lightweight, and they can sustain extremely high tension forces compared to, let's say, steel or something like that. They are highly flexible, and because of which they are very good in super strong fabrics, space elevators, and various other applications that you can think of. So, I hope I have convinced you that we need to go small. So, let me just take an example of a sand in the palm of my hand. I don't have hand here, but let me assume for the sake of it that it's about 4 millimeters by 4 millimeters by 4 millimeters. I think it's reasonable, right? You agree with me that I can hold about 4 millimeters in my hand, and if I were to do the calculation, assuming a density of 2.65, sand is basically silica, I will get about 170 grams of the material. And how big is a grain of sand? Possibly about 0.01 millimeters, and you can just think of it in your mind as a ruler. And then if I were to calculate the volume of each grain, it will be about, yeah, so they have sand here if I were to, but I do need also like a, I mean, I'm just measuring like this. So if I just take this one, you can see that I don't know if you can measure this, but if you can think of a ruler to measure how big this sand is, I'm assuming it's about 0.01 millimeter. I don't have the least count to measure that. So how many grains I would have? The volume of each grain would be about this. The total volume is about this, which I just now calculated. And so in our palm, if I were to say that I am going to program each grain of sand as a bit, I can hold about 6.4 gigabits of information on my hand. It's a large number, but not infinity. So now, if I were to actually harness the fact that each of these small grain of sand is made up of atoms, and yes, there are millions of atoms. You're very right. Actually, sand is silica, and if you know, I think most of you here know what is an Avogadro number. If you don't, you will learn it. It's just a number, but 1 mole of sand, which is about 60 grams, holds about 6.023 into 10 power 23 atoms. And if I were to calculate weight of each individual atom, it would be this much. So I will have this many molecules here. So not really a trick question, but kind of trick question. Which hand holds more, my left or my right? Oh, sorry, my left or my right? Any others? Right? I'll ask you to explain. Why do you think more? Right? Okay, why do you think right holds more? So left also there are many particles. Oh, hand side has more hand side. In case you are confused with the direction facing each other, this is the one I am calling it as right. Does it have more? Left has more. So you agree that left holds more information. So I will say it depends on how we read. Whether left has more, or I said it's not a trick question but a trick question. It depends on how we read. If I read the number of particles, the left, we just now did a calculation, it holds about 64 gigabits, and the right holds about 26.6 terabits, because I am counting the atoms, not the particles. If I were to count atoms in the left, then it will be 26.6 terabits times 64 gigabits. Okay? It depends on how we read. Okay, now that we know that when we go to an atomic level, can we really go there and do all this? What are the physical limitations? How small can we get? So how do you make these so-called nanocrystals? Why it is nano, I will come to it, but the first way of doing it is a very routine way. I can chip into it, I can grind it, I can cut a solid until it gets into a fine powder of nanometer size. Okay? So that is known as the top-down approach, and usually this is technically how it is done, lithography, wherein you kind of chip in all the various, you put in a beam and all that, and all of this is in nanometer length scales. Very accurately you can chip off that much material. And people have done, IBM was probably one of the earliest ones to show this. They have actually, these are at an atomic level, they have shown that okay, you can actually chip off at atomic level. So physically I can achieve it, but, and I can also achieve it the other way. I can start with a molecule and I can keep adding the molecules onto it, like growing it, and when it has grown to the size that I want, I can stop the growth, which is known as the bottom-up approach. Whether you want to do the first one or the second one is totally up to you. So how people do this is by colloidal methods. You just take a precursor and you thermalize it so that you get an active species, and they nucleate, and then they just start forming the particle at supersaturation, and then they grow, and you have these things on the surface which are known as the ligands. They provide resistance to aggregation, that they don't aggregate together and grow bigger, and they maintain the size. So this is how you maintain a bottom-up approach. So if you do that, you can get very interesting properties. Like for example, you can get fluorescence, you can use them as various, for fluorescence, for modifying the molecules in blood, you can do whatever. But you can also do nanoscale electronics. Let's assume that we have done everything in nanoscale. What are we going to get from it? That's the question, right? Just because I did something doesn't mean that you have to have an interest in that. So first I have to prove to you that there is an interest. So you can have nanoscale electronic, which has great thermal conductivity, high current densities, and you can have electronics like this, field emission devices, single molecular transistors, All of these things you can do. So this is from the, so far the limitations that I am talking about is from a physical perspective. I am actually like trying to see how I can cut it down and can I actually make them. How small can I get? I said I can do all of this, but most importantly when I go to this small size, what happens is the properties of this small unit is very different than larger units. Here is the surprise, surprise. Why should properties, I mean, you know that you have a nose, he has a nose, they have identical except for the size and they do exactly the same job. You have an eyes, he has an eyes, they do exactly the same job. Why should it depend on size? So this is where the concept of atoms come in, and typically what happens is we have these crystals. I come back to my crystals. I see that they are actually smaller in, you can see these, I will hand them out, I can hand them out, right? Yeah, so you can see the structure of these two are exactly the same. Why is it exactly the same? We will discuss. In the meantime, you can pass this along. You can see the two structures. And when you are done, give it back to me so that I can come back to the later part of that. Why is it exactly the same? Is because they are part of a unit cell. And what is a unit cell? A repeat unit. And this is sodium chloride. If sodium chloride, all of you know, is common salt, this is how it is arranged. They would exactly repeat. You can see one red, green, and this arrangement is the properties. Okay? And this is titanium oxide. Do you see that the arrangement of these two are very different? Yes? So the arrangements are very different, so that defines some of their properties. But why should it define the properties? What happens? Why should they be arranged in this format? So to say that, I have to tell you that although I am depicting it like one bead here, then this much space. Why it defines this much space? There is no this much space. What happens? This is just a model. The real life is more like this. This is titanium, this is oxygen, so on. Do you think I can fit in any more of this? Not really, right? So they are actually close packed. An atom would look like this, except for this hard, it won't be so hard, but an atom would look like this. And they would actually be, the spacing is defined by the size of each of the atoms. Okay, and that defines how they interact. And how they interact defines this thing and the next properties. So all of this is still, it still doesn't tell me why it should depend on size. Right? For have I justified why it should depend on size? No. I have just said like it will be a repeat unit, so you should not depend on size. Where does it start depending on size? So I also said that they are not hard like this. But for people who are close enough probably can see that they are actually like this box, if I were to call this as a box, is not exactly the size of this hard object here. You see there is this air which makes it bigger, and that is the sphere of its influence. Although the atom is of this size, the hard object is this atom, the sphere of influence is bigger. Do you see? Here rather, so this is my atom, these are my atoms, okay. Let us assume its influence would be this big, there is one atom inside, okay. And this influence depends on how big is this influence, I will talk about it, but if this influence is there, first thing you need to know is that this influence is there, and this in quantum mechanics is what is called as a wave function, okay. So now that you know that there is this influence surrounding this, Typically, these influences for semiconductors can range anywhere between 1 to 10 nanometers, and that is why nanometers are interesting. Why? See, this is the influence region, boxes of this size, and I have many atoms, but there are probably like 4 or 5 influence regions, right? But if I were to fix this in this box, or if I were to just, let me take the same one and I have a nice, okay, I will see this. We have not really tried out this experiment, but we have this iron powder. If it works at a later stage, Lakshmi will probably demonstrate it if it works as a science in action or some experiment, wherein if you actually, many of you might have actually tried heating an iron rod, nothing happens, right? But if you heat iron powder, you can actually see it. You have to take my word for it today that you can actually see this whole thing light up. And for more details at a later date, Lakshmi. Okay? So this is not the first time people have seen this. People have seen it as long ago as BC. So both, so we have now talked of all of these. Let us now look at what their structure is. So what happens is, what happens when I squeeze it? Let me see what happens at an electronic level, what happens. So you have an electron here, sitting here, and this electron, if I shine some light on it, will go to higher energy level, okay? And no electron likes to stay in high energy level, it wants to come down to the lowest energy at the earliest possible time. So what does it do? It emits all of this light and comes out. And whatever it emits is what you see as fluorescence, okay? Now I am telling you that I can actually control this distance by changing the wave function. And that distance is what I call the exciton binding distance. This is the distance that it requires to actually bind, and I will control that. And if I were to control that, first if it is way bigger than, I said this sphere of influence, right? This sphere of influence is technically known as Bohr radius, okay? So exciton Bohr radius, and that is the natural length scale of an electron and a hole. If it is bigger than that, I do not care, sizes are not going to change, okay? If it is smaller, then you can start seeing the effects of sizes. What happens is these continuous bands no longer remain continuous, they start becoming discrete, and one of the few equations which you do not have to worry about, it just says that the energy coming out of your system, which is this left hand side, is what it is in the bulk plus something else, okay? And that something else, which means that gap is increasing. That is all we need to keep in mind. So this is how, and if I can control that gap, I have already told you that if I can control that band gap, then I can control the fluorescence or the light emission. So this is what would happen, and this is technically how it would look like. This looks too technical, right? So let us watch if it is actually true, okay? Can somebody connect the chamber and show them these particles which are just different? You have to take my, oh sorry, you have to take my word for it that they are actually the same kind of particles, and we can have the lights off. So yeah, you can show them. Lakshmi, you can keep all of them so that they can see. You can keep them inside. It would be better inside. Inside. in the same order, so that the order was probably red to blue. This is the other side. You can see there, it shows better there actually, inside. Yeah, I think that one is the very light blue one. You can arrange them nicely so that probably they can all see. It's okay. I think that is in the UV region or very nearby the UV, so that's why you are not able to see that. But either here or there, wherever, I hope you can all see the same particles, the very same cadmium selenide glowing all the way from red to orange to green and kind of sky blue and a very UV. In between, blue is missing. What is tuning the gap? The size. Each of the crystal inside it is the size, is of a different size. So we just made different size crystals and you get these wonderful colors. For cadmium selenide, of course, if you are taking lead sulfide, it will go into the IR. It's not visually so nice, but it's still the same principle. So I am just looking at the visual colors. So can we have the lights, or rather just switch this thing? You can have the lights off, but just switch the thing to the computer. No, lights off. Just change it to the PPT. Yeah. So you can see that this is probably an image that you might have seen in the internet quite a lot, but today you are also seeing it here. This is same cadmium selenide going from, so I first showed you this absorption and the emission, which was not so appealing to the eye because probably you didn't understand what it was. But a small personal story here. When I was first doing my PhD, I was actually working on not even the visible region, in the UV region, and then I was doing an experiment. I just added zinc acetate with sodium hydroxide. What do you think should happen, zinc acetate with sodium hydroxide? You will form zinc oxide. Okay? It's as simple as that. And I was measuring absorption, which is just this. This white curves here is the absorption curves. And to my glee, I really was very excited. I am not exaggerating this. When I first did this, I was very excited. I was actually seeing it like I measure it after every 2 minutes and I see this absorption is getting more and more blue shifted, which means the size is getting bigger. I was actually thrilled to say that, oh, I am really seeing these particles grow, because I am actually seeing that absorption is shifting in real time, which was very exciting for me. So yeah, we can have the lights on. I'll leave it here, but we can switch it on later, because if you keep them excited for very long, it might lose the luminescence. So we will switch it on later if you want to get back to that. So where does this all come in? I cannot run away from this talk without bringing in the Nobel Prize of 2023, which was announced just a month ago, exactly on this day, which was actually given to these 3 people for first conceptualizing that in this size range. So there are these 3 people. The oldest is, I don't know whether he's the oldest, I think Bruce is the oldest, and Ekimo, they are about similar age, 78, 80 kind of, and the youngest is Bavendi. Ekimo was the first one to first put this together and demonstrate. It was actually given for the synthesis of quantum dots, and they actually, he put it together first in a glass, but in a very typical, he published it in a Russian journal, in a very typical Soviet US kind of relationship. Bruce was unaware of it. Bruce was in the US and he independently showed it for the first time in colloidal materials, that is they independently standing, meaning like this. And one of the people who was involved in this along with Alevisatos was also Bawendi. So now that this, so far we have never worried about size polydispersity. One of the particle can be 100, one of them can be 101, we do not care. But now suddenly we have to care. And first time they did not obviously get it exactly monodisperse one on the other, but it was Bawendi in one of his later papers who showed that you can actually synthesize them in a very narrow size distribution, and they were awarded this year, they will be awarded this year. So, it is very contemporary, they will be awarded this year's Nobel Prize for the synthesis and conceptualizing of quantum dots. And yeah, so now that we have quantum dots, and I have already told you what the size range is in the nanometers. I already also told you why this size range is important. Remember my smiley? The size range is important because this is the influence area of an atom, electron. So that happens to be in the few nanometers, and that is why the term nanoscience and nanotechnology evolved. And here size does matter, or the story of the least at last. So a nanometer is about 10 power minus 9 meters, which is about 10 angstroms. And when I say 10 power 9 meters, it is kind of difficult for you to imagine probably. So I just put, sorry, I pressed something wrong. Yeah. So average width of a human hair is about 100,000 nanometers, and a single particle of smoke is about 1000 nanometers, just to get a feel of how many particles we are talking about. And let us talk about the tools, because I told you that when I was doing this experiment, I was very excited that I am seeing these particles grow. And why was I so excited? Because I had a way of seeing it. So first just a few codes. By increasing by a factor of 10 the resolving power of a human eye, Galileo was able to discover Jupiter's satellite. The principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. This is not my statement, these were Feynman's statements. The problems of chemistry and biology can be greatly helped if our ability to see what we are doing and to do things at an atomic level is ultimately developed, a development which I think cannot be avoided. This was 1959, 1983, 1978 and 83, Bruce and Ekimov came up with these most recent things. And these are the length scales, because when I am talking, I am basically, an eye cannot really resolve. So I want to talk to you about it. So human hair, I already told you it is about 100,000 nanometers. I can resolve it using an optical microscope. I think all of you here know what is an optical microscope, right? So if I have to go beyond that, if I am talking of, I have talked about integrated circuits, lithography, so on. Most of those require an electron microscope. It is not a topic of today why optical microscopes cannot resolve, and I am not going to go into that detail. But if I were to go even further into atoms and molecules, I need a scanning probe microscopy. So let me just go over as to how to characterize these particles. First, as we all say, seeing is believing. So these are some images that were taken from electron microscope of these materials